You're here because you want to master Group 17 elements with a University of Cambridge graduate. This is actually part 3 of our periodic trends chapter. If you want to watch the previous parts or you want to watch the future parts, be sure to check out our playlist below. Hi, I'm Brendan and I'm a University of Cambridge graduate who has been teaching chemistry to many students like you over the past 9 years. I'm also the founder of the Chemistry Institution, where we have helped many students improve in a short amount of time and achieve the grades of their dreams. Be sure to check out our website in the link in the description below so that you can download a free copy of the notes for yourself and use it to run through this lecture with me today. So previously, we were discussing about periodic group and the periodic trends, as well as talking about the very specific properties of your group 1 elements, which are your alkali metals. And now we are going to discuss about your group 17 elements, which in other words are called your halogens. So these halogens have 7 valence electrons each, right? Because they are in group 17. And the halogens generally exist as diatomic molecules. Okay, this is a very important property that we have to know. Okay, your halogens exist as diatomic molecules, which means that each molecule consists of 2 atoms that are the same. Okay, so generally, for example, your chlorine, okay, they tend to be Cl2 for the molecule itself, or your bromine, these tend to be Br2, for example. Okay, your halogens are also so reactive that they are not found free in nature, right? Generally, your fluorine, okay, as the most reactive halogen, will combine with almost every element, including noble gases. Okay, so for example, hydrogen can easily react with fluorine to give hydrogen fluoride. As for your physical properties for your halogens, this is very important and you absolutely have to memorize this. Okay, you absolutely have to memorize this. So your halogens tend to be non-metals. Sorry, this is a typo. Your halogens also tend to have low melting points and boiling points. Not surprising because these are actually non-metals, right? And remember, these tend to form simple molecular structures. Recap to your chemical bonding. Okay, and these are also non-conductors of electricity. Again, not surprising because we know these tend to exist as simple molecular structures. And if you remember from chemical bonding, simple molecular structures tend to have or tend to be non-conductors of electricity. They also dissolve readily in organic solvents like tetrachloromethane. Okay, this in general is because, right, these halogens tend to be non-polar. Right, so they will easily dissolve in non-polar solvents. They wouldn't very easily dissolve in water, for example. Okay, and your chlorine, bromine, and iodine, these are all very sparingly soluble in water. Your halogens also tend to have similar chemical properties because again, this is tied to them having the same number of valence electrons. Okay, all of them have 7 valence electrons. So, number 1, they are very reactive nonmetals. Okay, number 2, they readily gain 1 electron to achieve a noble gas configuration because they all have 7 valence electrons and they only need 1 more to get 8 valence electrons. And they also have very strong oxidizing power. They are very strong oxidizing agents, and this is because they easily gain 1 electron, okay, to form ions with a charge of 1-. One of the key reactions for your halogens are your displacement reactions. And take note, these are very commonly tested in all your tests and all your exams. I can almost guarantee it will come out. Right? Displacement reaction is a very common reaction that comes out. Right? The key idea here to understanding what a displacement reaction is to just remember that the halogen higher in the group, okay, can displace a halogen lower in the group. Why? Because the halogen higher in the group is more reactive. The more reactive element, in this case the halogen, will displace the less reactive one. So for example, your bromine, right, can be displaced from a solution by the more reactive chlorine itself. So here we have a table that you absolutely need to memorize, right, of all the reactions between your halogens and your potassium with a halogen inside, right? In other words, the ionic chloride form. Okay, if you look at chlorine with potassium chloride, okay, since there's chlorine and chlorine, there's no displacement that happens because they are the same. But when you look at chlorine and potassium bromide, Okay, chlorine is more reactive than bromine, so chlorine is going to displace bromine from the ionic solid. So what is going to happen is, because of this displacement, right? Okay, your chlorine is going to kick out the bromide ion, okay, and the chlorine is going to be the ion instead, and bromine is going to come out in the diatomic form, Br2. It doesn't just come out as a single Br atom, it has to be in Br2, right? So because of this, we can find the observation, which is that a reddish brown solution will form, okay, because Br2 comes out, and we know that Br2 is reddish brown. If you compare chlorine, okay, reacting with potassium iodide, for example, chlorine is more reactive than iodine. So chlorine is going to displace iodine from potassium iodide. Okay, it was going to displace it from the ionic form. So your chlorine is going to react with the I- ion, okay, and the chlorine is going to become the ion itself. It's going to become Cl-. And the I is going to come out not as a single atom, remember, it has to be a diatomic molecule. So it comes out as I2. Okay, and because of this, you can tell what is the observation going to come out, right? So the I2, okay, is the black precipitate that forms from the reaction. Okay, so realize what I'm doing. Okay, I can postulate what reaction happens based on my theory on displacement reactions. I usually like to write the equation as well, and then from the equation I can easily tell what is the observation, right? Of course, you still have to memorize. In general, you must know that bromine is a reddish brown solution, and I2 is generally a black precipitate or black solid. Now let's take a look at bromine, okay, and reacting with all the ionic chlorides, all the ionic halogens. So bromine is going to react with potassium chloride first, okay, and because bromine is less reactive than chlorine, there is no reaction. Okay, bromine reacting with KBr, okay, there's no reaction is going to happen as well because it's just bromine and bromine, okay, and then bromine with potassium iodide, okay, here, right, a black precipitate is formed. Why? Okay, because bromine is more reactive than iodine. So bromine, okay, is going to react with the I- ion and displace it. So bromine will become the ion instead, okay, Br-, and I is going to get kicked out to form I2. Okay, and this is the black precipitate that forms. And if we look at iodine, iodine is one of the least reactive halogens. So iodine, okay, you compare it to potassium chloride, iodine is less reactive than chlorine because it's lower in the group, so there's no reaction. Same thing, iodine with potassium bromide, okay, it is going to have no reaction because iodine is further down in the group than bromine, and that's why iodine is less reactive than bromine, okay? And iodine with iodine, there's also no reaction over here. So here, hopefully you can understand, okay, the basis of displacement reactions, okay, and you can follow my line of logic, okay, to find out what observations would happen and what is the equation that you could write for the displacement reaction if it were to ever occur. Next, your halogens also react with water to form acidic solutions. Again, this is very important, okay, and these solutions will also have oxidizing properties. So for example, your chlorine, okay, can react with water to give hydrogen chloride, which is hydrochloric acid in water, and chloric 1 acid, which is HOCl, right? And this HCl is what makes the solution acidic because, okay, remember HCl is a very strong acid, okay, you can form H+ ions in water itself. Next up, your halogens also can react with alkalis to form salts and water. So this is something you have to memorize. So for example, your chlorine can react with sodium hydroxide to form sodium chloride, okay, NaOCl, and also water. And last reaction for your halogens, okay, your halogens tend to react with the more electropositive metals to form metal halides. So for example, when halogens react with alkali metals, okay, they form the alkali metal halides. So an example is sodium reacting with bromine, okay, when that happens, you will just get the sodium bromide, okay, and this reaction happens very easily, right? With transition metals, on the other hand, your halogens will form the solid metal halide of the highest oxidation state. So for example, if iron were to ever react with chlorine, your iron reacting with chlorine will give you iron chloride, okay, and it's iron what? It will be iron 3, okay. Between iron 2 and iron 3, we go with the highest oxidation state, so it's iron 3 chloride. So after discussing some of the reactions of your group 17 elements, we can start to talk about some of the changes of your elements when you actually go down group 17. Alright, so some of the changes include, alright, the halogens actually becoming darker, right? So if you look at the table below, your chlorine, okay, tends to be pale yellow green, okay, versus your bromine is reddish brown, and then your iodine is black. So the color is actually getting darker and darker as you go down the group. And just to be clear, you actually have to memorize all these colors. It is absolutely important. It will be tested, okay? And also, these elements in group 17 tend to change from gas to solid, okay? And this is because the melting and boiling points actually increase down the group. This is also very important to know. And your atomic radii will increase down the group. Not surprising as well, because the period number actually increases as you go down the group. Okay, you actually have an increase in number of electron shells. And lastly, the densities also increase down the group. Okay, so looking at this table, your chlorine tends to be a gas that is pale yellow green. Okay, as you go down the group, bromine actually becomes a liquid, okay, that is reddish brown, and then your iodine is actually a solid that is black. How about some of the chemical properties that change down the group? So your halogens actually become less and less reactive. Okay, take note, this is actually the opposite of your group 1 elements. Remember, in group 1 elements, right, as you go down the group, the metal becomes more reactive. In group 17, on the other hand, as you go down the group, the halogen is less reactive. Okay, so take note of this difference over here. So as you go down the group, you actually become a weaker oxidizing agent. And the reason is because it is more difficult to gain one valence electron, okay, because the number of electron shells are increasing. So the valence electrons are actually further away from the nucleus. Okay, so this is responsible for the decreasing reactivity down group 17. So just like before, we can easily use our knowledge that we found over here to answer general questions, right, that ask you to predict properties of other group 17 elements. And take note, this is a very common exam question as well. So how do we predict the properties of other group 17 elements? You need your knowledge from the known properties of your chlorine, bromine, and iodine, and also you need to know the changes down group 17. So let's take a look at an example question. So for this example question, right, it says predict the physical state and color of fluorine and what effect, if any, would fluorine have on aqueous sodium chloride, and construct the equation for the reaction, if any. Now, the first thing I'm going to do for this kind of periodic table trends kind of question is I'm going to scan the periodic table. I'm going to scan, okay, and find that, okay, fluorine is actually in group 17. Okay, so this is my first thing I'm going to find. This is in group 17. Okay, next, I'm going to find out where exactly it is in its position in the group, right? So fluorine is actually above chlorine, okay, and it's actually because of this, we know that this is actually more reactive than chlorine. Okay, so in terms of physical state, right, and the color, right, we know that as we go down group 17, right, the color actually becomes darker and darker. If we know that chlorine is actually a pale yellow green color already, so we should know that fluorine in general, the trend is that fluorine is very yellow green and it is also a gas. Okay, how do we know that it's a gas? It's because since it's above chlorine, it should have a lower melting point and boiling point than chlorine, and we know that chlorine is a gas already. So if you have a lower melting point and boiling point than that, you should most likely be a gas, right? Now in terms of the reaction with sodium chloride, right, because fluorine is more reactive than chlorine, we know that displacement will happen, right? So what's going to happen is fluorine is going to displace the chlorine from sodium chloride, and fluorine is going to take its position as the ion in now, and chlorine is going to get kicked out, okay, in a diatomic form. So your chlorine will actually be produced. So in terms of observations for this reaction over here, we know that a pale yellow-green gas is formed. Right? So that is exactly how we would answer a question like this. Okay, very last part. Okay, what are some of the uses of your group 17 elements? Right? So small amounts of fluorine compounds are actually known to be in tap water and your toothpaste to actually help prevent tooth decay. Okay, and for chlorine, on the other hand, it is usually put into your swimming pool water and tap water to kill germs and harmful microorganisms. So if you're a swimmer very often, you can maybe smell the smell of chlorine in the air, right? That's because the chlorine is actually in the swimming pool water, okay, to get rid of germs, okay, because so many people use the swimming pool and we don't want people to infect each other with their bacteria, all right? And for iodine, okay, you will see that there's actually very small amounts of iodine that are required in our body. Okay, you can't see it, but this is just a general knowledge that you can take in. And if you have a deficiency of this iodine, right, you will actually get this medical condition over here, which will result in swelling of the neck. That's all for today's video. If you really learned something and you like this video, be sure to click on that like and that subscribe button so you don't miss out on free content like this. If you want to join my community of students at the Cambridge Institution, be sure to check out our link in the description below so that you can sign up for a free trial class today. Here you can learn the exact systems that we use at the Cambridge Institution to help our students improve in a short span of time and also achieve their grades of their dreams in the end.